Hello, welcome to this MongoDB live talk. Today we're talking about a subject that some of you may have faced or may face in the future. Having multiple fields that have to be searchable and they share the same shape or structure, but you don't know them beforehand. This is solved by using the attribute pattern. However, with MongoDB 4.2, we introduced the Wildcard index as a way to deal with this situation. This is the question. Does the wildcard index make the attribute pattern obsolete? Let's find out. By the way, I am Gilberto Velasquez, MongoDB Senior Consulting Engineer for the US West Coast and Latin America. I have been working with MongoDB for 3.5 years. The overall agenda for the talk is the following. First, we're going to explain the problem, the situation at hand. Then, we will explore the current solution, the attribute pattern, see its definition, and then see how it performs. After that, I will introduce you to an enhancement to the attribute pattern and compare it to the baseline attribute pattern. The next step is to introduce you to the wildcard index, see how it works, and then contrast it with the attribute pattern. Finally, we will establish guidelines on when to use each approach. So let's talk about the challenge, the issue, the problem that requires to be dealt with. Disclaimer, I was not able to find interesting graphics or images, so most of the slides will be text, code, and numbers. A little bit on the boring side. Bear with me, please. You have broadly two situations. You could even argue that it's actually just one. The first one is searching in a number of fields that have similar structure. For this example, I took a video game I enjoy playing a lot, Age of Empires 2. Here, I made a document containing the release dates for its different versions. You can see those fields in yellow color. Release date original, release date HD, and release date DE. Here, the name of the fields is similar, release underscore date underscore, and then the name of the version. If a new version appears, we might add a new field following the naming schema with the release date for the new version. The second use case is a highly variable schema where you have a number of fields that can be different from document to document, but you need to search in all of them. In this case, I am showing what could be an entry on a collection of products for an online shop. The product shown is a laptop that happens to be the one I have for work. The new model has been announced a few days ago, and I renewed recently. Bummer. Again, the fields marked in yellow are the unpredictable fields, the features of the laptop, screen size, processor, and RAM size. If you had a different type of product, let's say a sweater or a jacket, the features would be completely different. You would have size, style, color, material, and on. The challenge is that all these fields are searchable, and we don't know what are the possible fields and values. Let's introduce the naive approach, how you would deal with this situation when you're inexperienced and eager to take on the world. The solution you may think of first is to create indexes for each field you know is being used. See the index definition in the first two yellow lines, an index for screen size and an index for processor. The good thing about this is that queries are still the same as usual. See the yellow line in the middle. Find where processor is Core i7. Here are the caveats. This approach simply won't scale if you have too many fields. If the fields are unpredictable, either you index in a reactive fashion, meaning you index after you notice a field is being used, or you try proactively by guessing field names. But there is a limit of up to 64 indexes per collection. Most of all, indexes are not cheap. An index requires storage, RAM, and CPU. The indexes have to be updated every time you insert a document, you delete one, or you update an index field. Usually, when you have 20 indexes or more, write performance is not acceptable. The attribute pattern. This is the way we have officially endorsed to deal with this situation so far. This is how a pro would do it. This pattern has been documented on the MongoDB blog by Daniel Kupal and Ken W. Alger. You can easily find their article by searching in Google, MongoDB attribute pattern. Pretty much likely, it will be the first search result. Also, Daniel is giving talks on schema design on MongoDB.live this year. I highly recommend you attend his talks. You won't regret it. The attribute pattern works by shaping similar fields or unpredictable fields using an array of subdocuments. Each subdocument has two fields, the attribute name and the attribute value. You can say each field and its value model as a subdocument is an attribute. We will refer to this type of fields as attribute for the remainder of this talk. Going back to the video game example, the release date fields are not grouped inside of a field named release_dates. Look at the yellow lines. This field is an array of subdocuments. Each subdocument has two fields. Version that represents the attribute name and release date that represents the attribute value. Given that the previous example had 3 release dates, the release date array will have 3 subdocuments, one for each release date. If we look at the laptop example, in this case, the naming is even more obvious. Given that I don't know a common field like in the previous example, I named the grouping field as attributes, just like that. And the documents have the attribute name as the K field and the attribute value as the V field, as shown in the yellow lines. Again, 3 fields translate into 3 subdocuments, as in the previous example. So, as you may already noticed, we're required to change the schema to use the attribute pattern. Each new unknown or similar field will be represented as a subdocument. This has an inconvenience, as your queries will become complex since you will have to use the $LMatch operator to find an attribute as shown in the first yellow line. If you need to find multiple attributes, you need to use the $AND operator, not shown here. Now, the attribute pattern has a huge advantage. It only requires a single compound index on 2 fields, attributes.k and attributes.v, as shown in the second yellow line. The write penalization will be lesser when compared to the naive approach, since only one structure has to be updated after inserting, deleting, or modifying fields. Be mindful that having unbound growing arrays can be considered as an anti-pattern, because you might hit the document size limit of 16 megabytes. Also, the more attributes you have, the larger the index will be. The read performance is surprisingly more nuanced, as it will depend on the query shape and the index fields. I would like to share a story, and what is actually one of the main motivations of this talk. Back then, in early 2018, we delivered consulting to one customer with approximately 20 searchable fields, and we recommended the attribute pattern. After a follow-up on 2019, the customer indicated the performance was not as good as just creating a bunch of indexes, like in the naive approach. I personally ran some testing, and to my dismay, I was able to reproduce the customer performance claims. Did we provide bad suggestions to the customer? I had to know, so I started digging into this issue to see if I could find a way to make the performance better, since we still stand on our position of not creating indexes carelessly. This is the setup I used to perform testing for this talk. I created several MongoDB Atlas M50 instances on AWS. These instances had 32 gigabytes of RAM and 8 dedicated CPUs, one instance per approach. The MongoDB version deployed was 4.2.5. I ran 10,000 queries per round per approach, meaning one run for the naive approach, one run for the attribute parent, and such. 7 queries ran in parallel, so I had one CPU available for the instance. Each query searched for a specific number of attributes, depending on the run. In cases where the run time went beyond 1 hour, I stopped the testing. The time when I stopped the testing depended on my mood, to be frank. Sometimes it was 1 hour sharp, some others 3 hours. I just wanted to have statistically significant results. I created a toolset to load data in different shapes for each approach, and also to run these queries. It is written in C# and compiled using .NET Core 3.1 and MongoDB driver version 2.10. You can find the toolset in the URL in the middle of the slide in green color. The dataset was 20 million documents with the same data shape, some fixed fields and attributes. By fixed fields, I mean fields that are non-attributes. They are non and present in all documents in the collection. They are fixed, they're not going away. These 4 fixed fields, there were 4 fixed fields and 10 attributes. The attributes were contained either on a subdocument or an array of attributes. I will show you the document shape in the next slides. The data size was approximately 7.65 gigabytes, which fits completely into the Wildcard cache, which is approximately 15.5 gigabytes of RAM for an M50 instance. This is the document shape for the attribute parent. As you can see, in the top we have the 4 fixed fields that are named field 1, field 2, field 3, and field 4. I am sorry for the lack of creativity with the names. Naming is a hard discipline. Then on the bottom in yellow, we have the attribute fields, which is an array of subdocuments. Each subdocument has 2 fields. K, that has the attribute name, and V, it contains the attribute value. Each document has 10 attributes. Okay, so this is the equivalent document using the naive approach. As you can see, the fixed fields on top are exactly the same. The attributes have been placed in a subdocument, and we have the attribute name as the name of the field, and then the attribute value as the field value. Again, each document had 10 attributes. It is worth it to mention that the dataset was the same for each approach, meaning an equivalent document existed for the naive approach and the attribute parent. The first set of tests, the test A, was querying for attributes only, meaning similar or predictable fields. For the attribute parent dataset, a single index was created with the fields attributes.k and attributes.v, as you can see in the first yellow line. The query shape, as I commented before, was an $sign and operator wrapping the $sign element matches of documents, one per attribute as shown in the lower half of the slide. The attributes were randomly picked, meaning each query had different subset of attributes, but all queries in a run had a specific number of attributes. To make the comparison with the naive approach, I created 10 indexes for each one of the attributes, as shown in the upper half of the slide. The query shape is straightforward, as shown in the bottom half. We have to use the dot notation because now the attributes are nested. Again, the attributes were randomly picked, and each query had different attributes, but they always had the same number of attributes within one round. Here are the results. As you can see, in this scenario, the naive approach is faster than the attribute parent. In average, by average I mean harmonic mean for simplicity, the naive approach is 85% faster. There are cases like the one for 3 attributes where the naive approach is 153% faster. Interestingly enough, you can see that there is a huge time difference between queries with 2 attributes and 3 attributes. 20 times the time required to finish the query. 2 attributes require tenths of a second, and 3 attributes require seconds to finish, in both cases. From there, time increases mostly in a linear fashion. Be mindful that for most applications, these times are not acceptable, as they are in the order of seconds. To make things more interesting, I added a more complex but closer to a real production workload, querying fixed fields and attributes, the test B. Document shapes were exactly the same both for the attribute parent and the naive approach. As a matter of fact, it was the same dataset but with different indexes and query shapes. In this slide, you can see the indexing strategy and query shape for the attribute parent. As you can see in the top yellow block, now the index has 2 fixed fields before the attributes. We will be querying using equality conditions on these fields. We're going to look for a specific value. We're not doing range queries. Consequently, the query shape changes, as you can see in the bottom yellow block. We have 3 fixed fields first. I added a third one so the query was not 100% optimized. Querying the attributes is done as usual, using the $and operator, wrapping $LMatch subdocuments. For the naive approach, I created 10 indexes, 1 per attribute, but each index has 2 fixed fields as a prefix, and then the attribute field, as in the first yellow block. The query shape is still straightforward, as seen in the second yellow block. We just add the attributes we want to search in the query, no additional operators. Now, this is where the results really shine for the attribute parent. In average, it's 4 times faster than the naive approach, with cases like querying 2 attributes, where it is almost 7 times faster. Also, as you can see, the times are significantly smaller than just querying attributes only. Worst case scenario is 4 milliseconds when querying for 10 attributes with the attribute parent, compared with 41 seconds the naive approach took to query 10 attributes with no fixed fields. Moral of the story: when possible, also search for fixed fields and use the attribute parent. Okay, so this is my personal contribution to the data modeling patterns, the quotes enhance quotes attribute parent, since it is not better in all aspects. Then again, I wouldn't be able to produce this contribution if it wasn't for the job of Daniel Kupal and Ken W. Alger. I thank them and I tip my hat to them as I stand on their shoulders. So what is the enhanced attribute pattern? It is the same schema shape as the attribute pattern, which I will refer as classic attribute pattern from now, but with a different indexing strategy. As you can see in the first yellow line, we create an index directly on the attributes field instead of indexing the attribute name and value. This implies that the query shape changes again. Look at the second yellow line. You have to query for a whole subdocument. This query shape has some inconveniences that we will discuss in a minute. Write impact will practically be the same as the classic attribute parent. Read performance will be top-notch for queries with fixed fields and attributes. In order to see the performance of the enhanced attribute pattern, I did the same 2 tests. As you can see, the index is really simple. Just an index on the attributes field. Then the query shape also simplifies. Instead of using $LMatch, we use a full subdocument. Remember that the number of fields, their order, and their values need to match. These are the metrics when I compare the 3 approaches when querying attribute fields only. Same methodology, same dataset. I took the attribute pattern as a baseline. As you can see, the enhanced attribute pattern is still slower than the naive approach, but the gap closes. In average, it is 33% faster than the classic attribute pattern, compared to the 85% advantage of the naive approach has. For a single attribute, the enhanced attribute is as good as the naive approach, but the performance decreases as we add more attributes to the query. When making the test for fixed fields and attributes, I create an index starting with 2 fixed fields and then the attributes array. The query shape simplifies again. First, we look for 3 fixed fields, and then we add a $sign and operator wrapping queries for full subdocuments on the attributes array. You can use the $sign all operator on the attributes field. The execution plan is exactly the same. For the metrics, I did not include the naive approach, as we already know that the classic attribute pattern was a clear winner. In this case, the enhanced attribute pattern has an edge over the classic one, on average 16%, up to 26% when looking for 2 attributes. When performance is your top priority, the enhanced attribute pattern is your choice. Sadly, there are some compromises that you have to make in order to get this performance. First is the fact that your schema becomes less flexible. The fields have to be exactly the same, exactly the ones that are in the attributes of document. No more, no less. And they have to be in the same order. The filter on the second. I need to repeat this slide, guys. Editors, I'm so sorry. Sadly, there are some compromises that you have to make in order to get this performance. First is the fact that your schema becomes less flexible. The fields have to be exactly the ones that are in the attributes of document. No more, no less. And they have to be in the same order. The filter on the first yellow line will work, but the one in the second won't. It won't results. This is because the way MongoDB compares subdocuments. Be mindful that if you update the subdocument, the field order may change. Also, in order to perform these queries, the driver needs to support field order preservation. This is the case for the C# driver and PyMongo. From personal experience, Java usually preserves it, but I was not able to find documentation supporting that fact. Also, there are certain queries that could be performed with the naive approach and the classic attribute pattern, like using comparison operators to make range-based queries. See the third yellow line. These are not possible with the enhanced attribute pattern. You have to make queries using operations different from equality, like ranges. The enhanced attribute pattern is not going to work. Finally, index size is around 25% larger than the classic attribute pattern. The Wildcard index. This is the latest built-in solution to this problem. It was introduced in MongoDB 4.2, and this is the mystery that we want to solve. Is the Wildcard index a be-all and end-all solution to this problem? Will it make the attribute pattern fade into oblivion? Let's find out. You can use the Wildcard index in the entire document or a subdocument. However, I am suggesting to group the fields that are attributes in a subdocument as shown in the yellow lines. This is a video game example. Same story with the product catalog, the laptop. We're grouping the attributes into a subdocument, putting the unpredictable fields inside of it. The Wildcard index does not require changes to the existing schema. As I recommended on the previous 2 slides, I recommend doing so. The query shape will be straightforward as with the naive approach. See the first yellow line. The index strategy will be simple. One index to rule them all, one index to find them, and one index to bring them all. The create index syntax is different from your usual index as shown in the second yellow line. As you can see, you need to specify the grouping subdocument followed by a dot, the $sign, and 2 stars. You could potentially index the entire document by just specifying $sign star star, but that is lazy schema design and lazy index management, in my opinion. Don't do that unless you have a legitimate reason. Performance. For writes is in line with the attribute pattern. And this is where things get interesting. Read performance is highly situational. In order to test the performance of the Wildcard index, we use the exact same document shape as the naive approach. But instead of creating 10 indexes, we created a single wildcard index for both test A and test B. There is a reason for that. We will discuss it in a moment. Finally, as expected, the query shapes were the same as the naive approach. When looking only for attributes, the wildcard index is significantly faster than the attribute pattern and the naive approach. In average, 143% faster than the classic attribute pattern. Also, this advantage is larger than the naive approach, which was 85% when taking the classic attribute pattern performance as a baseline. So, if you need to make queries only by attributes, the wildcard index is your go-to choice. On the other hand, when looking for fixed fields and attributes, the wildcard index is dead on the water. It's 3 or 4 orders of magnitude slower than the classic attribute pattern. Just take a quick look at the numbers. Worst case scenario, for 10 attributes, the queries using the wildcard index took in average 20 seconds, compared with 4 milliseconds on the classic attribute pattern. Long story short, if you need to query by fixed fields and attributes, do not use the wildcard index. The reason for these results is because the wildcard index is designed to only query for attributes, fields inside the attribute document. Wildcard indexes cannot be compound as of MongoDB 4.2.5. That was the reason we had to use the same index for test A and test B. Since the index won't have the data from the fixed fields, it has to read more documents from the collection, hence the slower performance. Summarizing, the read performance will be the best when querying only for fields on the attribute subdocument. We're wrapping up the session. You need the facts now so you can get your hands dirty making cool schema designs that will be web scale. Is the attribute pattern obsolete? So I guess we solved our mystery. No, the wildcard index didn't make the attribute pattern obsolete. Has the wildcard index failed? No, it hasn't. It works for the use case it was defined, looking only for attributes, and it rocks. Personally speaking, I see this as a win, as you have more choices in your toolbox, so you can get the best performance in most cases. You may have foreseen this outcome since I commented we were going to establish guidelines on when to use each approach, which lead us into the next slide. This is a comparison table featuring performance on querying attributes only, performance on queries with fixed fields and attributes, schema complexity, query complexity, and flexibility. I did not include the naive approach since it won't scale. Don't use it. You will have index management issues later. You have been warned. If you care about performance of queries on attributes only, your best shot is to use the wildcard index. You will get the best performance possible. Be mindful that once you have to query fixed fields also, you need to use some other strategy. If you need the top performance when making queries in both fixed fields and attributes, the enhanced attribute is your best choice. You're losing flexibility and need driver support. Finally, if you need a good performance all around, the classic attribute is your friend. Talking about the classic attribute pattern, it provides you with a way to make an unpredictable schema predictable. The queries become more structured but more complex. Using $& and operator and $& and ln match can be tedious. Indexing is simple and the performance is good enough in most cases. Use this when you need to boost your query performance while still being flexible. The enhanced attribute pattern is best when you need the best performance possible. Be mindful that you're losing query flexibility and capabilities, like non-range-based queries. Successful usage depends on driver support to preserve field order. Use this when performance is top priority. Postscript. Don't forget to test thoroughly. I don't want you to run into queries not return results because the field order is wrong, and then blame me for it. I won't accept that. The Wildcard index has the best performance when looking only for attributes, hands down. Your indexing will be simple, also your schema and your query shape. However, when making queries with fixed fields, it is not a viable solution. Use only when most of your queries are only looking for attributes. Well, this is it. I hope you found the session useful. I apologize for my bad English. I will be hosting office hours so you can ask questions around the attribute pattern, the Wildcard index, and the testing methodology. You can find information on the office hours on the mongodb.live website. It was my pleasure to share my findings with you. Thank you so much.